SwayamPrabha. Digital India. Educated India.
Okay, so let's start a new topic, stretching of circular sheets, and in this particular topic we are going to develop some models for evaluating some output properties, say for example pressure or force like that during stretching operations. And we have seen in the previous couple of classes about deep drawing and bending. Similarly, we are going to develop some models here also, and this is going to be a small section. Okay, and some theories which you already seen will be adopted here to develop such models. And whenever we speak about stretching of circular sheets, we can do that, actually practically speaking we can do that in two ways. Okay, one is by using punch, contacting the sheet. Okay, so punch along with other tools, in bracket I will write tools in general. Okay, so what you do here is there will be a sheet which will be grabbed on the die, and there will be a blank holder, and the punch will come and deform the sheet. Okay, and here the interface friction between the punch and the sheet is going to play a vital role in stress distribution or strain distribution, fracture location. Okay, the depth of fracture, the forming depth, all these things will play a your friction is going to play a big role in this. And though this is the case, of course when you use punch you can also change the friction, right. So depending on the lubricant you use, friction coefficient of friction that is prevailing at the interface, one can control such deformation quantities. Another way is basically with fluid pressure. Okay, so that means what? That means there is no rigid punch. Instead, we are going to deform the sheet with the help of fluid pressure. Okay, so the tools could be slightly different. So you can have maybe a die or an open die or a shaped die, and there will be a chamber through which you are pressurizing the fluid, and then that fluid is going to deform the sheet to take up the particular shape or a free shape. Okay, so this is what the main difference here. Of course, when you use fluid pressure, you can understand that there is no friction between the sheet and the fluid. Okay, so which is the main difference with respect to the when you use a conventional deformation of sheet with the help of punch. Okay, specifically in stretching. This using punch deforming the sheet, we already seen several examples. Though we have seen that in bending and deep drawing, and in the initial part of the modules, okay, we have seen stamping operations where punch has been used to deform the sheet. So we have seen that predominantly, and all those theories are valid here also, except that we have not seen anything about this fluid pressure based deformation, which will be the first part in this particular module. Okay, so the first heading is bulging with fluid pressure. Okay, bulging with fluid pressure, and this can also be called as hydrostatic bulge test. In short, they call it as HBT. Like uniaxial tension test we have, like UAT we say, similarly we can say hydrostatic bulge test. Okay, this is nothing but bulging of a sheet with the help of a fluid pressure. Okay, so this bulging with fluid pressure, if you use it as an experimental method to characterize the sheet properties, then this becomes hydrostatic bulge test. Otherwise, bulging with fluid pressure is a method to deform a sheet, and you can make any component shape with that. Okay, otherwise we can also characterize the sheet with the help of hydrostatic bulge test. Like your uniaxial tensile test we have, similarly we can use a hydrostatic bulge test. So the schematic is described here. So you can see that at the bottom there is a, let us say there is a die, and there is a retainer or a blank holder here you can say, and initially the sheet is, let us say, flat. Okay. Initially the sheet is flight like this, and then in between you give a fluid pressure, let us say P, that is a pressure with which your sheet is going to deform. That is the amount of pressure that you give, and let us say rho is the radius of curvature we have, and let us say at one particular stage your deformation height, your forming height is about h. Okay. So, you can imagine like there is a pressure versus height curve. Okay. You can draw a graph between pressure versus height. So, with increase in pressure what happens to height, that again that kind of characterization one can do, and you can say that A is basically this particular dimension from the axis to the clamping location here, okay, and R is basically any radius from the axis. R is basically any radius from the axis. Okay. So, I have written here that HBT is a common experiment used to characterize the material or a sheet, a stress strain response at higher strain levels. Okay. So, like in uniaxial tension test we characterize the material's stress strain behavior, but in that case basically you may get the sheet's characteristics only up to a particular limited strain value, let us say. Here you can get to a larger extent. Okay. So, you can deform a material, the same sheet, let us say aluminum or steel. If you do it with the HBT, you can get a stress strain response to a larger extent, to larger strains. That is the main advantage if you speak it in terms of characterization. I think we have seen this briefly in the formability test. Okay. In one particular chapter we have seen this. Anyway, so let us come back to this. You can see that it is made up of a metal sheet here. Okay. This is your sheet. It is partially formed sheet that is inserted in a die with a circular aperture. So, die has got a circular aperture here, that is at the center you can see there is a hole, and through which the material is going to deform. Okay, and it is secured and deformed using an internal pressure, okay, that is IOS pressure P. Okay. So, and of course, our main focus is basically this A region. Okay. On both the sides you can say A region, and let us say a sheet thickness is T. Okay. So, you can pick up this A region only, and we can show this kind of diagram about your state of stress. We know that already, like sigma theta is basically your one of the principal stress, and sigma phi is going to be another principal stress. Okay. So, sigma phi, sigma theta are already known to us. Okay. So, your sigma theta is on the circumferential direction, and sigma phi, we said that in the deep drawing the sigma phi was represented as a cup wall stress, stress in the cup wall, sigma phi we represented. A similar one you can see the direction, it is in this particular direction as compared to sigma theta, and sigma 3 is always there, perpendicular sheet thickness, otherwise sigma t, that also can be seen. So, these are the stresses acting on at any element in this particular deformation zone, that is A zone on both the sides. Okay. So, the sheet is bulged to a spherical shape by a fluid pressure. So, you can imagine that this particular shape is approximately spherical shape, you can imagine like that, and if you look into the state of stress and strain, okay. So, we are going to concentrate mainly in this pole region, this topmost point in this deformation zone, no, this is called the pole. Okay, this is called pole region. Okay. So, if you look into the state of stress and strain in this pole region, that means you are going to take an element from this and you are going to see what is the state of stress and strain. Of course, you will have sigma, the same thing will happen, sigma phi will be there and sigma theta will be there. Okay, corresponding strains also will come into picture, and at this location if you see, you are going to have sigma phi and then sigma theta, which is related to sigma phi by alpha into sigma phi. Okay. And you have a sigma t, which is nothing but our sigma 3, which is going to be 0 because of plane stress assumption that we are doing right from the beginning. So, you can get the nomenclature, what do you mean by sigma phi? Sigma phi is like sigma 1, sigma theta is like sigma 2, sigma t is like sigma 3, which you are regularly following until now. There is a slight change here. Other than this, everything is same. So, now if you look into the pole, okay, this pole region, it is characterized by alpha is equal to 1. What I am saying is, in the pole region, if you pick up an element here and see what is the relationship between sigma phi and sigma theta, they both are equal. Sigma phi is equal to sigma theta. So, basically we say alpha is equal to 1. We say alpha is equal to 1, we say. So, when you say alpha is equal to 1, I am going to write sigma theta is equal to sigma phi. Directly I am going to write. So, that is one important thing. So, now if you know if alpha is equal to 1, what is beta, that can be calculated again by using Levi-Masser's flow rule, it is equal to 1. Okay. So, and I am going to write epsilon phi is going to be there, and epsilon theta would be equal to beta of epsilon phi, which is going to be epsilon phi only, and epsilon t can be written either as ln of t by t naught, right, t by new thickness divided by original thickness at any location. Okay. And if epsilon theta is equal to epsilon phi, then you can write epsilon t as minus 2 epsilon phi, minus 2 epsilon phi. We have already seen this already. So, you can get epsilon 1 plus 2 plus 3 is equal to 0, and in that two strains are same. So, epsilon t or epsilon 3, okay, nothing but epsilon 3. Epsilon t would be equal to minus 2 times epsilon phi. Okay. So, this is what is main important state of stress and strain in hydrostatic bulging. Okay. And just to extend this point, we have the procedure of evaluating sigma bar and epsilon bar also for any situation. We have seen that several times. In this case also we can get sigma bar and epsilon bar. So, we can use von Mises effective stress equation, which we have derived before. I just written here for your convenience. So, square root of 1 minus alpha plus alpha square into sigma 1 is equal to sigma f, which is also equal to sigma bar only. So, what will you get as sigma bar is, if you put alpha is equal to 1 here, it is going to be equal to sigma 1, which is nothing but my sigma phi. Okay, you can directly write here. And if you put beta is equal to 1, 3 will be cancelled. So, you will get 2 epsilon 1, okay. So, which is nothing but epsilon bar is equal to 2 epsilon phi. 2 times epsilon phi is nothing but minus epsilon t. So, you can write minus epsilon t, right. 2 times epsilon phi here is minus epsilon t, okay. So, you can get minus epsilon t here. So, in hydrostatic bulge test, or when you stretch a sheet with a uniform fluid pressure P, okay, then we can write sigma bar is nothing but sigma phi only, and epsilon bar is equal to 2 times epsilon phi, which is nothing but minus epsilon t, right. So, of course, one can see what is the comparison with respect to uniaxial tension test. Okay, uniaxial tension test, one can get what is alpha. So, alpha is sigma 2 by 1. So, alpha is going to be equal to 0 in UAT. In UAT it is going to be equal to 0. Then what is beta we can find out, and we can also get such relationship for uniaxial tension test just for comparison, right. So, that is one thing. So, this is one important result we have here. So, now our main aim in this particular module is to get this P. What is the, can we derive an equation for P? Can we derive an equation for, simple equation again, okay, no complexity, there is simple equation for P. Okay. So, for that what I am going to do is I am going to use an equation which we already know, we have not derived in this particular course, we have not derived, but I think we have already known that your this kind of stretching of or deformation of circular shells or circular sheets, we can relate sigma phi equal to sigma theta, because alpha is equal to 1, which will be equal to p rho by 2t. Okay. I think we have already studied this probably in solid mechanics, one can look into it. So, sigma phi is equal to sigma theta is equal to, because alpha is equal to 1, will be equal to p rho by 2t, and all our usual definitions, p is your pressure and rho is indicated in the diagram, and t is your sheet thickness. So, this is one result, we will come back to this. Okay. There will be some small equation we are going to substitute here, but before that we can also see how strain distribution is happening. Okay. How strain distribution is happening when you see the deformed sheet from the pole to A region along radius. Okay. Pole means this is the pole, to A region means in the gripping region. Okay. So, from pole to this A, from the gripping region, this from A distance, okay, in the radial direction. So, along radius we are going to see how strain distribution is going to vary. So, naturally we have only two surface strains, in plane strains. One is you have epsilon phi and epsilon theta. From these two we can get epsilon t. Okay. So, we are not going to include that here. So, you will see that from pole, which is at the center here, to A, which is a gripping region, we have seen that you have of course same epsilon phi and epsilon theta at the pole region. Why? Because it is beta is equal to 1. Okay. The membrane strains, or you can say the surface strains are equal at the pole, okay, where R is equal to 0, okay, where your R is equal to 0 if you put here. So, both the strains will be same. Why? Because beta is equal to 1. Now, at the edge of the sheet, that means when you are coming here at the edge of the sheet, this is your edge. It is clamped, no, it is clamped. So, the circumferential strain at the edge is 0. The circumferential strain at the edge is 0. So, you will see that your epsilon theta will go to 0, but epsilon phi will have some value. Epsilon phi will have some value. Okay. So, epsilon theta, so the one corresponding to this will be 0 at the edge, and this fellow will have some value, which is what is given in this particular graph. Okay. And you will see that from the top two, from the pole region to A, both the strains are going to decrease. Both the strains are going to decrease. Okay. Which means when you do a fluid pressure based deformation of sheet, or which is equivalent to saying a frictionless case, totally frictionless case, then there are chances that your surface strains, in plane strains are going to be maximum at the pole region, and it is going to diminish when you move towards when you move away from the pole. Okay. So, this region is of focus to us, that is why we always bother about pole. Okay. So, your strain is going to be maximum at the pole region if it is a frictionless case. For example, if it is a hydrostatic bulge test, then you can expect peak strain at the pole region, and it is going to diminish in this way. So, epsilon theta will be 0, epsilon phi will have some value. So, what is the importance of this particular test? So, the primary justification for employing this test lies in its ability to induce substantial strain in materials with minimal strain hardening even before reaching failure. Okay. So, it means that suppose if you take a material with probably it has got minimal strain hardening, suppose ductility itself is not that good. So, getting its characteristics, stress strain characteristics using uniaxial test could be very restricted. Okay. In such type of materials also you can use this hydrostatic bulge test, okay, and you get sufficient stress strain data before failure happens. And this particular FLD we are aware of that, okay, it is between epsilon 1 versus epsilon 2, in this case basically epsilon phi and epsilon theta I have drawn, and this is your typical forming limit curve, we know that, right. This is your typical forming limit curve of that any material you can imagine. Okay. So, your of course, we know that in this hydrostatic bulge test where the strains are equal, beta is going to be 1, then your strain path is going to be orange color 1. The bulge test will follow this particular strain path or mode of deformation, and it will reach forming limit curve at this particular location. Okay. And there you are mentioning these two limit strains as epsilon theta star and epsilon phi star, like epsilon 1 star and 2 star. No? We are aware of this nomenclature. What is it from our instability chapter? Okay. So, you will see that it is going to reach your forming limit curve along this. Now, on the other hand, when you speak about uniaxial tension test, which is on the leftmost, on the second quadrant on the left side, you will see that the material is going to follow this particular black strain path and is going to reach your forming limit curve here. Okay. But we also know that tensile instability occurs at, let us say, epsilon u is equal to n, okay, which is going to be somewhere here. Necking in the tensile test may start here itself, okay, and you will see that this value is going to be larger than this value. Okay. Your bulge test value is going to be slightly larger than this fellow. So, in a way you can say that okay, the membrane strains at the point of failure under biaxial stress, that is in bulge test, denoted as epsilon phi star and epsilon theta star in the FLC figure, surpasses the strain observed at necking in the traditional tension test. Okay. In this way, one can understand that when you do hydrostatic bulge test, there is a little advantage even for low ductile material, that you can have a stress strain behavior comfortably, which is not possible in your conventional uniaxial tension test. And this I already mentioned. Okay. So, it becomes apparent that effective strain equals twice the membrane strain experienced during biaxial tension, which is not the case in uniaxial tension test. In uniaxial tension test, you can find out what is the value. We already done that before. Okay. So, because of this small advantage, other than uniaxial tension test, if you want to have good fit for your stress strain curve, okay, beyond your tensile fracture, okay, then one can go for this kind of hydrostatic bulge test. Fine. So, now let us try to get an equation for pressure, a simple equation for pressure, okay, which is not again very accurate. It is going to be an approximate model, but it will give you a quick feel for what would be the pressure and how to calculate it. So, here again we are going to consider bulging of a circular Iverton diaphragm. It is like a sheet only, thin sheet you can imagine, okay, and we are going to develop an approximate model for that. So, with respect to the previous figure, this particular figure you can imagine, this particular figure, okay, we can write this area of deformed surface is 2 pi rho h. So, rho is the your bend radius and h is the deformed height. If you multiply that 2 pi times, then you will get area of the deformed surface, that is one. So, you want to equate volumes before and after deformation, we can do that. So, initial one is up to clamping region. So, naturally pi a square T naught, initial thickness is T naught, new thickness could be T, okay. So, you can say 2 pi rho h into T if you get it. So, you will get T as T is equal to T naught a square by 2 rho h, okay. So, a is a constant, we know this, a is also fixed, rho may change with respect to a and h, okay, and your h will anyway change, your height is forming height will anyway change. So, now again as usual we are going to consider sigma bar is equal to k epsilon power n, let us say, and we can write in a simple equation sigma bar is equal to, the sigma bar is nothing but sigma phi which we already derived, right. Sigma bar is equal to sigma phi, no, sigma bar is equal to sigma phi already derived. So, sigma bar is nothing but sigma phi equal to k, epsilon bar is, this fellow is nothing but, what is the value epsilon bar? Epsilon bar is nothing but minus epsilon t, right, minus epsilon t, epsilon bar is nothing but minus epsilon t. So, which is nothing but ln of T naught by T, which is nothing but ln of T naught by T, it is generally T by T naught, but minus. So, you, because you have minus, I am writing ln of T naught by T power n. This will be useful for us. We are going to simply put this equation sigma phi into the previous equation for pressure. Okay. So, now pressure to bulge diaphragm is given by, we are going back to this equation. So, P here is nothing but my 2 sigma phi T divided by rho, right. P rho by 2T is sigma phi, right. So, P is equal to 2 sigma phi T by rho, right, 2 sigma phi T by rho, and what I am going to do is very simple. So, in place of T which is a new thickness, I am going to put my previous equation, T is nothing but T naught a square by 2 rho h, T naught a square by 2 rho h I will put, and finally I will get this equation, and instead of that I can write sigma bar a square T naught divided by h rho square. So, finally I will get this equation for pressure, T is equal to T naught a square by 2 rho h. So, T naught a square will remain here and fine. So, and you will get this particular equation, and the only important points that you should like some couple of important points that you should note here is, like in the previous equations which we derived in the previous chapter, your sigma phi, either you can take a constant flow stress or you can make it as a function of strain. So, in a way you can consider strain hardening. If not, you can have an average flow stress also, like what we have seen in deep drawing, and the only concern is this rho. So, this rho of course can be, if you can relate it to A and H, then it becomes all known values, all known values. So, that one can get it. Otherwise, from this you can get a graph between P and H. One can get a typical characteristics of P and H, right. Okay. So, now as I said, when the sheet is bulging, the pressure may peak at dP is equal to 0. This is what I was telling you. So, if you get P versus H, there will be one peak, let us say for example something like this, I am just randomly drawing. So, at this location you will see dP is equal to 0 we can put, after which bulging will continue with the decreasing pressure gradient, because it indicates something is happening in the material. It could be instability, okay, just due to pressure, without any friction. So, which means that when the strain at the pole approaches forming limit as shown in forming limit curve earlier, rupture will happen. So, we have fixed that fracture is going to happen at the pole region, and fracture is going to initiate there, and if you put an instability condition like dP is equal to 0, okay, so you can compare these two cases, like when is your strain going to reach your forming limit curve, like we have shown here, this particular point, and when dP is going to become 0. These two can be compared to quantify your instability, but it may so happen that your limit strain may reach FLC little after dP becoming 0, little after dP becoming 0. Okay. But if you consider this diaphragm or sheet as a load carrying member, then you have to be very careful that maximum pressure point constitutes instability and fracture. Okay. For maximum pressure point, no, this particular point is actually should be the deciding criterion for if it is a load carrying structure, or if you are deforming it, one should see the difference between dP is equal to 0 and when epsilon 1 star and 2 star is getting reached. So, one has to be careful in these two. Otherwise, for hydrostatic bulge test, a simple equation for P is obtained by sigma bar, which can be related to your epsilon. As a function of epsilon, you can say A square T naught by H rho square. So, now with this simple analysis, let us go to stretching over hemispherical punch. Okay. Now, fluid pressure based deformation is done, let us say same material is actually stretched over a hemispherical punch, like what we have seen in limiting dome height test, which you have discussed in the formability chapter. So, similar situation is shown here. You can see that the sheet is held in this particular location. Okay. So, and there is a hemispherical punch. The punch has got a hemispherical end at this particular location, you can see, and all the values are given here. Okay. So, you will see that the sheet is actually getting deformed, and one thing which you should know here when you deform it using a punch is interface friction. What is this fellow going to do? Okay. What is this fellow going to do in this interface? That is very important for us to know. And you pick up an element as usual, like the way we discuss generally, you pick up an element here in the deforming zone anywhere, maybe here or here, anywhere here, but little away from the gripping and the pole region, and you plot the tension here. Okay. So, your normal pressure P is going to act on the sheet element, and your T phi is going to act in this way, and T phi plus dt phi is going to act in this way. This is similar to what we have seen in simplified stamping analysis. A similar diagram we drew, similar one here. Okay. And because of P, you have mu P here, which is nothing but your effect of friction comes into picture. Okay. So, there is some change in tension, which is on one side it is T phi, the other side it is T plus dt phi. Okay. So, we know that the sheet tension escalates proportionally with the displacement of punch, right, because it is gripped in these two regions. So, naturally when you make a punch to get displaced in this direction, the tension will actually escalate, it will increase, right. So, now when you pick up a frictionless case, in scenarios where there is negligible friction between the sheet and the punch, the highest strain emerges at the pole as shown in this particular figure. Okay. The same figure which I have used before, the highest strain emerges at the pole as shown in this figure. So, this is where you have highest strain. So, because it is going to have a larger strain, we expect a failure also to happen in the pole region through like maybe tearing or splitting, like that. The material will tear apart in this particular location F. So, it is very simple. So, strain distribution for frictionless cases, already we know that. So, failure is going to get initiated at the pole because there strain is going to be larger as compared to other locations. So, now if you do not put lubricant, this is a frictionless case, no? Frictionless case means you put lot of lubricant. Okay, lubricated, let us say, I am writing, well lubricated, let us say. Okay. Frictionless case means well lubricated. Okay. So, now there is another case where there is no lubricant, okay, or a dry friction, maybe you can say, the case with friction. So, now this frictionless case is a little impractical actually. There is going to be friction, whatever lubricant you can put, okay, then there is going to be, it is going to be challenging to keep it frictionless, otherwise one has to go for hydrostatic bulge type. So, presence of friction, okay, it may change certain strain patterns in the sheet, strain distribution in the sheet, which is what very crucial for us to know what is it. The strain distribution epsilon phi, okay, is plotted with respect to R, okay, from pole to A, let us say. In this, two are compared. One is without friction, blue color, the other one is with friction, red color. Okay. So, that is what I have shown in the second point. Due to the influence of friction contact stress, that is mu p, just now we introduced this mu p component here. Okay. Because of this mu p, it is going to, this mu p, this is going to actually pull the point of maximum tension, okay, away from the pole region. Okay. So, this mu p, what is going to do is, because, okay, it is available somewhere in the deforming region. Okay. If you see this, because of the presence of mu p, okay, in the case with friction, this is going to actually pull the maximum strain from the pole, towards some other location away from the pole. Okay. So, that is the main job of this mu p here. The point of maximum tension and strain is located away from the pole region. So, which means if you draw epsilon phi from pole to A, then it will follow this red color pattern. So, it will be having some value at the pole region, and at a particular location, let us say your R, let us say, it will be maximum, and then again it will diminish. Again it will diminish. So, when compared to without friction case, this is very different. You will see that. So, the peak value is going to happen not at the pole, but little away from the pole. This much distance away from the pole it is going to change. Okay. So, whereas this is the pole region. That is the main function of this friction. So, this specific location becomes the anticipated failure point susceptible to splitting. So, now here in this case you can see F here. Here in this case you can see F here. Okay. So, with friction failure is going to happen little away from the pole region, maybe at R distance, when compared to the case without friction, where failure is going to happen at the pole. So, you can also see that maybe this fracture, this failure location could be circular in nature. Okay. So, you can see from the top view, you can see from the top view that this R location is going to be there at any radius in the circular diaphragm, isn't it? So, it may split, depending on how instability develops, it may split in the entire ring of the circular path, okay, between the peak and the gripping region, somewhere in the at a distance of R it will fail. This is the main difference between with friction and without friction case. Okay. So, let us come to the effect of punch shape. What is this punch going to do? So, we are taking two extreme cases. One is a flat bottomed punch. Flat bottomed punch means like this. Okay. So, there is a vertical portion of this punch as usual, and there is a small corner here, and the bottom is flat. Okay, bottom is flat like this. There is a small corner, bottom is flat. Okay. So, in this diagram you will see that there is one upper figure and lower figure. Upper figure is going to tell you about thinning distribution, okay, with respect to R. Okay. So, that means when you move from pole to, that means let us say from the topmost point of the sheet, let us say for example from here, okay, to this particular region, how thinning is going to change, epsilon t, thickness strain, but we have put minus here. So, how thinning is going to change is what is shown in the upper figure, and lower figure is going to tell you two different stages when you have with friction and without friction. Okay, two things are shown here actually. So, this is a flat bottomed one, okay, with friction and without friction. Okay. So, and you will see that this thickness strain distribution is not same. Okay. In one case you will see that it is going to peak somewhere here, in the other case the peak is somewhere here. Okay. The peak value on the with friction case is going to be larger as compared to without friction if you go for flat bottom case, because your mu is going to play a big role only in the corner region, nothing much will be there in the flat region. So, I am saying the friction is limited to radius of the punch corner in the flat bottom punch. Radius of the punch corner means this radius, no. So, it is limited to that particular location. Okay. This prevents the material from being stretched over the flat face of the punch as a result of increase in tension there. So, naturally tension will be more in this particular location, and hence your face region may not play a big role in stretching operation. And what will happen here is, since your friction is going to play a role only in the corner region, okay, in with friction case, that means less lubricated with friction case, you will see that thinning is going to dominate in this location as compared to the other case. So, at the same stage, okay, you will say the thinning is going to dominate. So, naturally what you can do is, so obviously in without friction case you can go for larger draw, larger stretching as compared to with friction case. As a result, maximum depth or forming height that can be reached is lesser in the case of with friction. That is why I just made this difference. You can see this difference. No? This difference comes into picture mainly because in the frictionless case, that is on the left hand side, okay, you may have reached a larger forming height. Okay. Maximum depth can be reached is lesser in the case of with friction case. Okay. That main reason is the corner region, because there is a lot of friction, the corner region thinning will be dominant in this location as compared to the other one. So, now if you move to the other one, pointed punch or hemispherical punch, something like that you can imagine, then the situation is shown in this diagram. A similar diagram, thinning is plotted with respect to your radius, and you have two locations, one is left side, okay, and then the other one is right side. So, right side you see that friction is available, that is with friction, left side is without friction. In this case it is actually opposite, in this case it is going to be opposite. Okay. So, if it is with friction, okay, that means your mu p is going to be there. Okay. Then we can imagine that your strain distribution, thinning distribution is going to be something like this. Okay. Though we know that your peak is going to be away from the pole region and it is going to be lower as compared to the case in the left hand side, that is a case with without friction. Okay. So, this is going to have better forming height as compared to the other. So, pointed punch has an opposing effect. When there is no friction, that means on the left hand side, the stress is focused closer to the nose and depth before failure is constrained. Okay, that we already studied. Friction has the effect of reducing the tension at the nose and dispersing the strain across a larger area, allowing for deeper forming. So, it will not allow, okay, your strain to concentrate in a localized region, okay, like in the pole. Rather, what is going to do is it is going to distribute the strain uniformly when compared to without friction case, and hence you will see that the peak strain is going to be less as compared to this value. You see it is going to be less. So, you may have a larger forming height. So, your friction and shape of punch is going to play a significant role in determining the forming height and strain pattern and localization of strain and fracture and failure. Okay, one has to be careful. Okay, in flat bottom punch, how to manage mu, okay, how to manage lubrication, and in a pointed punch like hemispherical punch, how to manage mu, friction, one has to be little bit be aware of what is the change. So, before we complete this particular section, let us see a small subsection, stretching of a sheet with a hole. Stretching of a sheet with a hole. So, okay, we are not going to derive any equation, rather we have seen some of this before and we have just picked up the details, and let us try to understand some important parts here. So, stretching of sheet with a hole means what? Suppose you have a sheet, okay, and then you are stretching it, that we have already seen. Let us assume that you have a sheet and there is a hole at the mid, there is a central hole, and that has been grabbed and stretched like this. A simple schematic I have drawn here. Let us say this is your let us say this is your punch, this red color one, no? Let us say this is your punch. Okay. So, let us say this is your sheet and there is a hole at the center, let us say like this. So, a hole radius, let us say Ri, and let us pick up R naught as a reference radius for us. Okay. At R naught radius, there is a tension T phi that is acting on the material, T phi that is acting on the sheet. So, you are stretching it with the help of T phi applied tension, okay, and hole will actually expand. Okay. So, this what we are studying is applicable for hole expansion test. So, hole expansion test, I think we already discussed in formability chapter. Basically, it is a formability test which will tell you the deformability of or formability of the hole. of the entire sheet along with the hole. So, when your hole is going to crack and formability will be stopped, will be over, is what you can find out from hole expansion test. There are standards available, but here we are just giving you a schematic. So, a circular blank with a hole stretched over a doomed punch is shown, the hole radius is Ri and T5 tension is applied as shown. Okay. So, now at the edge of the hole, okay, when you see this edge is what is going to crack, fail, it should fail, okay, with the deformation, right. So, if you see T5, how is it moving, how is changing from this particular location R0 to Ri, okay, R0 to Ri, you will see that T5 must be 0, okay, at the edge, because it is actually a hole itself, okay, and a state of uniaxial tension in the circumferential direction would exist as per Tresca yield locus. Suppose if you follow Tresca yield function, okay, then your T5 is 0, which means that there is going to be only one stress, which means that it could be uniaxial in the circumferential direction, okay. And these tensions can be plotted in Tresca in the first quadrant as shown in this particular right side figure, okay. So, I have drawn a tension locus, tension basically, instead of stress based yield locus, I am drawn a tension locus. I think we have studied this at the end of your second chapter, okay, where T1 and T2 can be used to draw a locus like sigma 1 and sigma 2. So, instead of sigma 1 sigma 2, I have just drawn here T1 and T2, which is nothing but T theta and T phi, okay, and I have just drawn the first quadrant, which is what is interesting to us, okay. So, that is why I mentioned a part of second quadrant and a part of fourth quadrant here. So, this is your first quadrant. So, the first quadrant for Tresca is shown here, and you will see that when Ri at Ri is here, Ri location, that is at the hole edge, is here, where T5 is actually 0, where T5 is actually 0. That is what I mentioned as T5 has to be 0 at the edge, okay. So, this is nothing but your T bar, okay, or other words you can say Ty, yield tension, or T bar, okay. T bar is what we have seen in the previous chapter, the redrawing chapter. So, T bar could be your yield tension, okay, when this locus is actually getting satisfied. So, when you move from Ri to R0, so R0 may not be equal to T bar. So, this height is T bar again here, this height is nothing but T bar, it may not reach T bar, okay, it will be here in this location, and here you will see that there is going to be some T phi and there is going to be some T theta. So, that will be the situation of your hole and away from the hole with respect to tension. So, now if you want to derive a simple equation for this tension T phi, I want to get this T phi, okay, we can apply force equilibrium and we can find out, but what I would show here is we will use this differential equation which we have already derived in deep drawing process, and we are just going to simply follow that, okay. So, in the deep drawing we already derived that, you remember that we consider there is an element in the flange region, okay, and then we apply force equilibrium along the radial direction. So, all these calculations we can get, and you can see that d sigma r divided by dr plus sigma t by t dt by r minus sigma theta minus sigma r by r equal to 0, okay. And we also said that this term will be 0, why? Because we said t is not going to change, t is equal to t naught, in that this fellow will become 0. So, what I am going to do is this part I am removing, okay, I am going to use this and this, I am going to just rewrite it for this particular hole stretching problem, and I am writing in terms of tension I am writing. So, dt phi divided by dr minus d theta minus t theta minus t phi by r equal to 0. This part is removed, everything else I am just keeping as it is, which I am going to rewrite again as dt phi by dr minus, instead of t phi I am going to write t bar, okay, minus t phi divided by r equal to 0, everything will remain same. This fellow is going to change, why? Because this t theta can be equal to t bar, okay, at Ri. So, I am going to write this. So, I am just given a hint here, tensions in the sheet are T phi and T theta is equal to T bar, okay, and T theta is equal to T bar, okay. So, now I am going to put a boundary condition and I am going to integrate it. So, what is the boundary condition? At r is equal to Ri, T phi is equal to 0, right. At r is equal to Ri, my T phi would be equal to 0, and if I integrate it, I will get a simple equation T phi is equal to T bar into 1 minus Ri by R. Ri by R. What is Ri? Is this? R is any radius away from the axis. Okay. So, the above equation can be drawn schematically to show tension distribution during hole stretching, which is what I have shown here. Suppose if you plot T versus R, you can see that, so again as I said, T phi would be Ri. At Ri, if you see, it would be 0, that means at the hole edge, and it will increase until reach a point at R naught. Okay. And T theta would remain almost constant at one particular value. Right. So, this is one way to analyze it. Now, what is the similarity with respect to circular blank without a hole? Okay. In circular blank without a hole, we know that T phi is equal to T theta. Right. Why? Because we already said sigma phi is equal to sigma theta. Why? Because it is alpha is equal to 1. Same thing works out here. T phi is equal to T theta. So, this can happen from the tension locus figure. We can say that this can happen, this can occur only if these two are equal to T phi. Only if these two are equal to T phi. Otherwise, this cannot happen. Right. And it is also obvious, because when you say alpha is equal to 1, put it in that equation before, okay, you will see that this fellow will lead to sigma phi equal to sigma theta is equal to sigma bar, we said. Instead of that, we are writing T phi equal to T theta is equal to T bar. Okay. So, now this differential equation, what will happen? Here this also will go off, this will be removed. Okay, you can simply say dt phi by dr equal to 0. Dt phi by dr equal to 0. In fact, you can also try with respect to maybe you can use in this case we said alpha is equal to uniaxial, no, in this case we said alpha is equal to 0. You can say for example, if we say at the edge, okay, T phi is equal to 0, then it may reach the other one, T theta would become T bar, right. So, that can be obtained even if you take some alpha value. If you assume uniaxial alpha and then you put it in the 1 minus and find out, you may get this. You can try that. Anyway, so now this equation we are getting, so only difference here is only the first part of the previous equation comes into picture, circular blank without a central hole, which is nothing but the previous one, a conventional stretching. So, this indicates that T phi does not change with radius, and hence the stress distribution is uniform, which follows T phi is equal to T theta is equal to T bar, right. And this is what we also got before, sigma phi is equal to sigma theta is equal to sigma bar equal to P rho by 2T. So, with respect to your stress distribution and tension distribution, you can check the similarity between, okay, or you can make a case, a sheet with a central hole and sheet without a central hole. You can make a case between these two, you can compare these two and one can understand these things. Okay. So, we stop here, we again discuss in the new thing in the next chapter.